All right. Well, thank you again to the organizers for organizing this conference and having me here to give this series. I know you're a little bit behind schedule and probably everyone's eager for their coffee break. I hope that this last talk should be fun. So today I'm going to talk more about those non-crossing arc diagrams we saw in the last talk and the connection to some dynamical combinatorics. Okay, I'll go ahead and start. So I'm going to move here you go. As you know, I'm like annotating my tablet here at the same time. So if you see me looking down, that's why. I'm looking at my notes to make sure we're all in the same place. So we've done a lot of stuff this week. I'm sure there have been many wonderful lectures, and today, right, our goal is to talk about some dynamics related to the Tamari lattice and continue to survey some of the great people working in this area. Okay, so specifically, I'm going to tell you about a kind of game you can play. This sort of originated with permutations in the weak order, and it's called pop stack sorting. But we're going to mainly think about this. So everything will still be in type A, although results here are going to be in general about finite Coxeter groups. So we'll talk about the Tamari lattice and then sort of generalize to Cambrian lattices. And you've actually seen an example of a Cambrian lattice in my previous talk, but I know I wrote that word on the slide, but maybe didn't say what it was. Okay. The very end, if we have time, we'll talk a little tiny bit about some representation theory connections. And I'm going to introduce you to one final important person in my kind of mathematical growth, which is Jessica Stryker. So I want to talk about dynamical stuff, and you probably are familiar with Jessica. She's a professor at North Dakota State, and she's one of the in my mind, one of the founders of this field of dynamical algebraic combinatorics. And with Nathan Williams, she has explored the connection between like the Kreverick complement for non-crossing partitions and row motion on like order ideals, say for the root poset, and has generalized this in lots of cool and interesting ways. Inspired, like, since I'm talking about Jessica, I wanted to mention, although this is not really the point of my talk, I wanted to just mention that semi-distributive lattices actually have a really nice kind of row motion operation on them that comes from the edge labeling by joint irreducible elements that we've been playing with. So we saw that this edge labeling can tell you when you're semi-distributive, or at least joint semi-distributive. We've seen that the edge labeling in the specific case for the weak order also tells you about lattice quotients. And now today, this is very brief, and I just want to show you this game that you could play and ask some interesting questions about, but then not really engage with it. We're going to go in like a different direction. Okay, so let's zoom in. Here's how the game is played. You pick an element. So let's say, for example, 2, 3, 4, 1. And you know what? Actually, I'm gonna do 3, 2, 1, 4. And what you do is you look at the edges below it and the labels you see there. And so those labels might be in some terms of some combinatorial object, like these arc diagrams, but they could, but essentially they're the joint irreducible elements of your lattice. Okay, so I see my edge labels. They're these arcs, and I can even kind of let you like label them more clearly for you. So there's an arc which connects the second and third nodes here, and an arc which connects the first and second nodes. And what I do is I look for the unique other element in this poset with precisely those labels going up. Okay. So if I zoom out, maybe you see which element that is. It is actually this guy here. And so we could say row of 3, 2, 1, 4 is going to give you 2, 3, 4, 1. Okay. There's a version of this which is completely like analogous, where instead of doing down labels, you take the up labels of an element and look for the unique element, which has those as down labels. And oftentimes that is also called row motion. I'll do one more example. So at the very top, I see these 3 down labels. So you look for the unique element with precisely the same up labels. And actually, there's only one element which even has 3 up labels. And it's way down here. And we can see that they are exactly the same arcs. So row of 4, 3, 2, 1 is 1, 2, 3, 4. Okay, so that's a game that we can play on a semi-distributive lattice, but I'm going to do something a little different, which is actually related to this row motion operation. And this is called pop stack sorting. So I'm going to first tell it to you on just the level of the permutations, where it has a really nice description, and then we'll talk about what this means in terms of the lattice structure, since we've been talking a lot about lattices. Okay, so I hand you a permutation in one-line notation, and then pop reverses each maximal descending run, but it doesn't change the position of those runs. So for example, if I have 4, 2, 3, 1, I see a run 4, 2, and then the next term goes up. So that's the end of this descending run. And I see another run 3, 1. And what I do is I just swap those, I reverse those descending runs, but I don't change their order. So the 2 and 4 will still be in front of the 1 and 3. And that's what happened in the next step. So the 4, 2 becomes 2, 4. The 3, 1 becomes 1, 3. Got my permutation. And now I look at the next, I look like for all of the descending runs in the next permutation, there's actually only one, and it's just a descent. So I reverse it without moving around where the 1 and 4 are in the, like with respect to the other entries. And now I have 2 descending runs again, 2, 1, and do blue 4, 3, and I reverse those, and finally I'm at the bottom. When everything is in order, when you're at the bottom element of your weak order, we say that you're sorted. So this is like from computer science. You have some list of things, you want to put them back in order. How are you going to do it? And there's lots of algorithms. And pop stack sorting has been around for a while. So I'll talk a little bit about the history. But I just thought we could find this element in the weak order to sort of see what that orbit looks like under this operation. So let's see here. We were looking at 4, 2, 3, 1, which is right here. And then when we popped, we reversed the descending runs. And we go down this sort of polygon face to 2, 4, 1, 3. And then we go down this edge. And we're at 2, 1, 4, 3. And then we go down that polygon face to the bottom. So there's my orbit. Okay, so the reason I'm showing you this is to highlight or motivate this kind of equivalent definition. If you're in any semi-distributive lattice, or really any lattice where you can take meets, you can play this game. So pop down, what you're going to do to compute pop down in a lattice is you take your element W, you look at all of the things below it, kind of like row motion. We were doing something very similar for row motion, except now you're going to take their meet. So maybe this is U1, U2, U3, U4, and I take the meet of these U's. And then, so that's what's in this set here, but now I have an additional W hanging around, which seems like you don't really need it. Once you've taken the meat of the things you cover, like, why are you taking an extra W in there? It's not doing anything. So the reason why that extra W is in there is if W happens to be the bottom element, then typically we interpret the meat of the empty set to be the top element. And we kind of want this operation to take us down monotonically in our lattice poset. So we wouldn't want to do this pop stack sorting on the bottom element and somehow get flipped back to the top. That's not what we want. And to prevent that from happening, we do, when we take pop of our bottom element, we get the meat of the empty set, which is problematic. So we just meet it with also the bottom element, and that keeps us stuck at the bottom. Okay, so mostly that extra W doesn't do anything except when you're the very bottom element. And I guess this definition makes it sort of clear. Pop down takes us monotonically down in L. Okay, so let's revisit the example we were just looking at. Oh, you know what? I have one extra thing I want to say since I was talking about row motion. If you're in a semi-distributive lattice, or I have a typo here, more generally, if you're a semi-distrim lattice, which I'm not going to define, then pop is related to row by just taking an extra meat. So we actually saw an example that row motion may not take you down in your lattice. Pardon me. But pop always does. So as an example, we saw that when we did row motion of 3, 2, 1, 4, it didn't take us down. It took us to something that's not comparable. Right, so pop and row motion are not the same, but they're very close to being the same. And sometimes they are the same. When row motion does take you down, it's the same as popping. So as a, while I'm on this page here, we saw that when you pop, when I row 4, 3, 2, 1, I get 1, 2, 3, 4. We saw that. But also, if I pop 4, 3, 2, 1, what am I going to get? I'm going to take the meat of those coatoms. And this is a little bit hard to check if we think about meats. But if you think about reversing descending runs, it's very clear that popping down, I only have one descending run and I reverse it, I get all the way down to the bottom also. So we see sometimes pop and row give us the same thing, and they give us the same thing when row motion actually does take you down. Okay.
Emily, can I ask a question?
Yes.
This theorem of Colan and Williams, can we characterize row motion by the first property? I mean, if you take pop of W and decompose as W means something, should be row motion W?
That's a good, I think that's true. I think that what you're I don't know if exactly what you said was correct, but I think you're right that you can kind of characterize row motion in terms of pop. And they may have this. So Colin and Nathan have a section of their paper that's like totally all about how to connect these two operations. So I think it's worth, they have this probably written down. Okay. You want to look for a statement that you're interested in.
Another question.
Sure, yes, go for it.
What does the last line mean?
Ah, yes, thank you. Oh, Jen, no, sorry, this typo is really bothering me. So the last line says, great question, because we're going to talk more about this. The last line says that, what if you want to know about the image of pop? Okay, so pop, now think of pop down as a map, which takes you from L back to L, not everything is in the image. So what's in the image? It's exactly the things which are bigger than rho. So if you apply rho and you go down, okay, these are not exact, sorry, I've misspoken. There's a bijection. There's a bijection between the set of things where if you do rho and actually get smaller, those elements correspond to elements in the image of pop. So this is this last line is connecting the image of pop with rho motion of some of the elements. Yeah. So we're going to talk more about the image. This is actually one of our main questions, is trying to understand the image of pop. Seems very elementary. Okay, so in the context of permutations, a permutation is called p pop stack sortable if it takes p times to get p iterations of this pop map to get down to the identity. So I kind of like to pause here and ask a question, two questions actually. One, what's the longest do you think it can take? What's the longest? Let's say in S4. So we're looking at S4 here, and I can zoom in so you see this weak order a little better. There we go. What do you think would take the longest to pop? Like maybe you even have an idea of like an example. So that's one question. And then my second question for you is, how many, like, can you identify them? But also there's a nice enumeration. How many elements actually just take at most one iteration of pop to be sorted? Okay, sorted means you're at the bottom. So that means you apply pop and you're there. You're at the bottom. How many elements have that property? Okay, I want you to just like stare at the weak order for a minute, turn to your neighbor, do a little think, pair, share. Like, what do you notice? Can you find something that takes the longest to be sorted? How long does it take? And how many things do you think, or can you just identify some of the things which take just one iteration of pop to get down to the bottom? All right, I'm going to give you like a minute to think about that. You can shout stuff out, but maybe talk to your neighbor first. Don't give it away to everybody. Yeah, okay. I see some people like turning to their neighbors is good. I think maybe. I can't hear you talking to each other, so I'm just hoping.
Oh, that's not true. No.
Yeah. Related to that question. More than for.
You take any partition in intervals.
Second question?
Yes.
Second question is easy. Do a composition or whatever.
Yeah.
It's about to do the one or thing.
Okay.
Minus one.
Now there's conversation happening. It's very nice to see. So what did you find something that you think would take the longest possible time to sort? Like have a way to think about it? You're not sure? Do you have a guess?
No, no.
I can't. You're gonna have to talk really loud for me to hear. I know. Sorry. I know there's somebody here who has a guess for what might take the longest to sort.
Or for the second?
Maximum run, all the using run now flip them.
More than 4.
One go.
What do we think? Somebody has to be a spokesperson for me. Give me an idea. What do you think could take the longest to sort?
What about the example that you just did? Would that be the longest?
That is an example of something that takes the longest. Yes, that's right. So one example would be 4, 2, 3, 1. It's sort of hard to see I mean, to me, maybe you just do enough examples, you're like, I can't get any more than 3 iterations here. I think it's really helpful to think about an element like what? Okay, all right, so we're gonna zoom in a bit. I think it's helpful to think about this guy, 2, 3, 4, 1, because it's frustrating. Every time you do pop, almost nothing happens. Just 2 things move, right? First, the 4 and the 1 swap, but then you're not done. Now the 1 and the 3 have to swap, and you're still not done, right? You're like moving as slowly as you could possibly imagine, because you're moving all the way from the very back to the front, and you can only move 1 step at a time. And to me, that's a kind of helpful example to think about, like, oh yeah, there's sort of no way to be worse than that. Yeah, so everybody takes no more than n-1 iterations of pop. And I find it helpful to think about the things which have like the n and 1 descent all the way to the right. How many things do you think take at most 1 iteration to pop? Do you have a guess for how many, or do you want to shout out a couple that you noticed?
Just 2.
No.
There's more than 2, but we know for sure the top goes down to the bottom immediately, right? The bottom also counts, so there's 2. But can you give me like 3 more?
The guess was n choose 2, not 2, by the way.
Oh, n choose 2. Thank you. Oh, that's a good guess. I kind of see why you guessed that, but it's not correct. You're like thinking about pairs. You're like, well, what if there's just like 1 pair and I just have to undo them? So I'm going to give you another example that takes only 1 iteration to pop as a way to illustrate. That guy, 3, 2, 1, also has 1 descending run, goes all the way to the bottom in one step. By symmetry, the guy on the other side, right?
It has to be this.
I think I may have heard the right answer, but I really wish I could be in the room with you. But I see you're thinking about it. It's good. Then this guy here is very similar, right? 2, 1, and 4, 3 takes 1 iteration. The other things which are somewhat more obvious, if you're super close to the bottom, you like have nowhere to go, right? All the atoms take 1 iteration of pop. I think maybe we got them. So we have these three atoms here. Then there are these 3 kind of longer descending runs that are above them. That's 6. Plus the top and the bottom, that's 8.
With n-1.
Yes, there you go. Yeah, good. 2 to the n-1. So the n-1 is coming from all of the pairings you can make from consecutive numbers like 1, 2, 2, 3, the simple generators, right? And then the 2, the reason it's a power of 2 is you're just sort of taking any subset of those and you're going to put them together to make these descending runs of consecutive numbers. And then when you swap them, when you reverse those, like you're just immediately at the bottom. And I feel like thinking about it as reversing descending runs could be slightly confusing. I mean, maybe that makes sense to you, but it's also very clear to me when I think about that lattice theoretic definition, because I'm sort of the top of some like standard parabolic subgroup. So when I take the meat of the coatoms there, it makes sense to me that I'm going to end up at the bottom. Okay. Oh, that was fun. So pop stack sorting has been around since the 1970s, sort of initiated by Ungar here, who showed that it doesn't, it takes at most n-1 iterations to sort any permutation. And then there's been a bunch of more recent results about pop stack sorting. So there are generating functions for counting the number of things which take 2 iterations or p iterations in general. They satisfy a kind of nice recursion from where using this recursion, you can show the generating function is rational. But I don't believe there's really a nice formula for counting them when you're talking about pop stack sorting on the entire week order. There's also a recent paper that describes the image of pop on the week order. This has a really nice description in terms of sort of like overlapping descents. And then Colin Defont and Nathan Williams have extended this to these semi-distrim lattices, and week order fits within that, and so does the Tamari lattice. And then we're going to talk about Cambrian lattices as well. And I should also say that the work that I'm sharing today is based on joint work with Colin Defont and Eric Hansen. Okay, so that's some of the history of pop stack sorting. And as I said, we're going to focus actually on these c-Cambrian lattices, which I think you heard in Christian Stump's talks. He's mentioned c-Cambrian lattices, and we kind of saw a sneak preview of them in my previous talk about kind of lattice quotients in the Tamari lattice. So these generalize the Tamari lattice. To make a c-Cambrian lattice, it's kind of the same data as for a non-crossing partition lattice. You need a Coxeter group, really a Coxeter system, and a Coxeter element C. And then, and from that data, you can define a Cambrian lattice. These lattices have many nice properties. They are a generalization of the Tamari lattice. So there's also semi-distributive. Was considering putting this in here. I'm going to just add this in case this is meaningful to you. They're also trim, which is a nice lattice property. They have connections to non-crossing partitions. As you've seen in cluster algebra's representation theory, there are Catalan many elements in these lattices. So there are things that I care about, and hopefully you can care about too. Okay.
Emily, can I ask something?
Sure.
Can you tell us anything about the generating function of the number of pops that you need to go down?
I do not. I can share with you I can post a reference for it on the Discord.
Great, thank you.
Sure, of course. Yeah. Okay, I think there was another thing I wanted to say about Cambrian lattices, and it's completely, oh, okay. I think what I wanted to say is that I'm going to share some results with you about Cambrian lattices for general Coxeter groups, but what I'll talk about, like the examples I'm going to give you, will be all in type A. So just a little heads up. So we have built a lot of nice machinery for the type A. Okay. So one example of a Cambrian lattice is the Tamari lattice. So I'll put this here. This is our Tamari lattice friend that we've been following along. And I wanted to do an example of popping here to illustrate something. So let's pop. Who did I want to pop? I wanted to pop 3, 2, 4, 1. Okay. So if I do pop down 3, 2, 4, 1, what happens? I guess I'm supposed to reverse my descending runs. So I get 2, 3, and 1, 4. Oh, is this the one that I wanted to pop? Oh, no, I'm sorry. I made a mistake in my notes. I apologize. I really wanted to pop, I think, this one. Yes. All right. So back up. Pop down of 2, 4, 3, 1. I should reverse my descending run. 2 is not a part of that descending run. Okay. I am so sorry. This is the guy I want. Yes, yes, yes. This is the one I want. Okay, okay. Let's pop down 3, 4, 2, 1 by reversing our descending run. I only have one. The 3 is going to stay in the front. 4, 2, 1 is my descending run, becomes 1, 2, 4. But I look for 3, 1, 2, 4 in this poset, and I don't see it. Right, and then we remember, oh, right, these are exactly, so this is missing. And the problem is these permutations, these are exactly the 3, 1, 2 avoiding permutations. And when I tried to do our reverse descending run pop, I accidentally got one of these patterns that I was supposed to avoid. So what I'm trying to illustrate here is we cannot do the naive kind of reverse descending run pop in our Tamari lattice and expect to get something that we can work with. Instead, we really have to use that lattice theoretic definition, which is look at the covers below you. And take their meat and that should be what my pop is. Okay. And if you're wondering, why did she pick so many of the wrong ones? I kept picking ones where I wasn't breaking the pattern. So I apologize that I had missed, I wrote down the wrong permutation in my notes. Okay, so I'm gonna make one observation here. Pop down in our Tamari lattice is not going to be the same thing as popping down in the weak order. They're going to be different. And one of our questions, so I told you that the image of pop in the weak order is pretty well understood and has a nice description in terms of sort of overlapping descending runs. But the image of pop in the Cambrian lattices in general is not known. A lot of like the dynamics that are known for the weak order haven't been studied in Cambrian lattices. So the Tamari lattice, oh, you know what? That's right. I'm going to give you guys a chance to think about this.
Excuse me, I have a question.
Oh, yeah.
In your example, you don't get the permutation, but you get the permutation which is the same congruence.
That's true. You're right. Yeah, and so that is one way to get.
Will you always get it the same?
Yes.
Okay, it's not really different.
Yeah. So what you, yes. So I think the question is like, oh, but what if I really really want to do the reverse descending runs thing? One thing you can do is you can just reverse the descending runs in your pattern avoiding permutation and then project down to the bottom element of your class. And that will give you pop in a Cambrian lattice. So there's one way to get a handle on pop here. So we're going to look at the kinds of questions we've already asked for the weak order. What's the image of pop in a Cambrian lattice? We'll talk about the Tamari lattice first. How long does it take to pop, like to sort things in a Cambrian lattice or the Tamari lattice? We know the answer in the weak order. Can you find something which takes the longest time? Could you count those things which take the longest time? These are the types of questions we're interested in. So let's talk first about the image of pop. And I'm wondering, can you find, this is a little more of my interactive stuff. Can you find two things that are not in the image of pop in our Tamari lattice? I don't know, turn to your neighbor, think about it. I know you can find one thing that's definitely not in the image.
There the permutation and the theorem in the last point. The permutations that the non-crossing link theorem. The last one is.
I can hear that somebody's talking, but I really can't tell what they're saying.
Ones where you have the last point and the first point connected by an arc.
The
and
last
then-
one.
Oh, that's so, yeah. You're like, you have the theorem. That's wonderful. Okay, so you're saying, for example, that like this one, definitely not in the image.
But I mean, the four ones that are at the top cannot be in the image. Yeah.
Yeah, you're kind of, and maybe what you're thinking about there is like, they take the longest to sort. How could they possibly be in the image? I think that's a really good observation. There's more stuff that's not in the image. Another one that's not in the image is the very top. Like, how could it be? Who's gonna go? Pop takes you down. There's nobody above. So that one's also not in the image. But yeah, there's more, and there's more things even where the 1 and 4 are not connected, or even the 4 is not involved in a descent at all. So as an example, this guy, not in the image. But it's a little hard to check, you know, like you're looking at this and you kind of have to look at everybody above and be like, okay, how could I get down to this thing? Yeah, it's not an easy thing to just check. But some known results about the Tamari lattice is that W is in the image of pop if and only if the last entry is n. Maybe this is what somebody was saying and I didn't hear it properly. And also you have no descending runs with more than 2 entries. So actually, let me go back up. This guy almost looks like it could be in the image because the last thing, the last entry in the permutation is n, it's 4, but the descending run is too long. I have 3, 2, 1 instead of just a descending run with 2 entries. So this would be not in the image. But an example of something that is in the image would be this one. Yes, in the image. And who goes to it? That one. Okay. It's also known that it takes the same amount of time to get sorted in the Tamari lattice as it does in the weak order. It still takes n-1 steps. And how can you tell when you're one of those worst case scenarios? It's when the 1 and n are together in a descent. Because that's that situation where you're just gonna move the 1 over as slowly as possible that I had hinted at earlier. Okay, so these are some known results, and we're gonna generalize them for the Cambrian lattices. Here, and I will highlight, since I have it here, some of these things which take the longest to sort. Maybe as an exercise, you can count them. They have really nice enumeration. So if you're bored and you don't want to listen to the rest of my talk, you could just draw all of these arc diagrams, which have a longest arc. You're gonna see these have a nice, there are 2 of them here. Okay. All right, so let's dig into what makes the Tamari lattice the Tamari lattice. You know that it is a lattice quotient of the weak order now. We've been able to see them. We know that all of these elements in the Tamari lattice have these arc diagrams where the arcs all go to one side. There's a nice map to non-crossing partitions that I showed you. And one way you can think about that fact that all of the arcs go to one side is that for all of the numbers 2 to n minus 1, we've made a choice. We've said that you can never see a big number, a small number, and then a medium number somewhere later. And the medium, these 2 to n minus 1s, these are kind of playing the role of a possible middle number. Right? So we've made a choice. We're saying this is never allowed. We're never allowed to see that any one of those 2 to n minus 1s on the right side of any descent. And you can actually do the opposite choice. You could say, I actually want to disallow a medium number from being on the left side ever, and you'll still get a Tamari lattice. And so what we do for a Cambrian lattice is we make a similar type of choice. In type A, for every possible middle number, so 2 to n minus 1, we're going to say, okay, 2, you are a possible middle number. I'm going to pick a side. You're not allowed to be on that side. So as a concrete example, I could say 2, you're never allowed to be on the right side, ever. 3, you're never allowed to be on the left side. 4, you're never allowed to be on the right side. I mean, I can make any choice, left or right. I'm just giving you one concrete example where I switch back and forth, back and forth. So I can do any variation on this. And that pattern avoidance condition is going to give me a Cambrian lattice, which is a lattice quotient of the weak order in the same way that the Tamari lattice was. So I want to kind of come back to that connection between arcs and lattice quotients we talked about last time. Okay. So in this slide, I'm summarizing that left-right choice that I'm making for each middle number as like a vector. So maybe if I put all possible middle numbers, say on one side, they're never allowed to be on the right side. I might encode that with a vector of like, say all zeros. Maybe zeros mean no right side. And then all ones would be the opposite. And if I swap back and forth, then I'd get a vector that looks like this, where I see no right, no left, no right, no left. This swapping back and forth is a special Cambrian lattice called a bipartite Cambrian lattice. Okay, so let's look at that bipartite example where I said, all right, 2, I don't want you to be on the left side. I'm going to disallow all of the arcs where 2 is on the left and 3 is on the right. Well, I hope I didn't swap this in my notes. Let's see. But yeah, let's look at this. What would this mean? I don't want to ever see 2 on the left. So I'm going to draw this red bar that's bad. And 3 on the right. These are arcs that are breaking this rule. You know what? I think I maybe have this swapped. Let's be consistent. We'll see how I did this on the next page. Oh yeah, okay, good. So I'm gonna get rid of anybody who's breaking the rule for me, where I have 2 on kind of the wrong side, where my arc is going through this red bar that I've created. So the 2 that you see here, my disallowed bar, I have an arc going through it. I'm going to get rid of those. And I similarly get rid of any of these longer arcs below. And I'm just going to show you that actually this is an order ideal in this subarc poset. And we said that every order ideal of the subarc poset is actually giving us a lattice quotient. These become the arcs that I get rid of, and everybody else I'm going to keep. Here's a similar flavor. Oh, I think I got just, here we go. And here's where I'm getting rid of exactly the arcs from those pictures, although I didn't label it on the, I didn't label the edges here. So this is the resulting lattice quotient I get from following this pattern avoidance condition. Okay. And if I now contract everybody down to their bottom endpoint, which I'll go ahead and circle these for the congruence classes, which are non-trivial, this is the resulting quotient. And here I have drawn in the arcs that I get. Okay. So our main result says that if you hand me any Cambrian lattice, and I think maybe something I'm not making clear, which I had written in the slide, but I didn't say it out loud. That choice of 0, 1 vector, of left versus right, of disallowing, is exactly the same data as this Coxeter element. So if you hand me a Cambrian lattice and I want to know about the image of pop, here's what I'm going to do. First, I'm going to look for a special element which I call PI. PI is the greatest element above the simple generator SI, which is not above any of the other simple generators. Okay. And now I can tell whether I'm in the image of pop if I like this third one the best. So I'm going to describe this third one. If W is not above any of those PIs, and if I look at the interval W to pop of W, what I see is a Boolean lattice. This Boolean condition turns out to be the same as saying the descents of W commute.
Emily, one little question. How many times do you think you need to finish?
Oh, yes. Do I get to go? Oh, how?
So,
Yeah, how much time do I have?
tell me the time, but if you need the 1 or 2 more minutes.
You started
Oh
late.
no, I went much slower than I expected. I had like 10 fewer slides, but I'm.
You had already did the 45 minutes, but I don't know, if you think that you can round up in a couple of minutes.
I can definitely, you know what? We made it to my main result. I want to give you some examples of it and then I'll be done. So I think I can be done in a couple minutes.
Okay, thank you.
I forget, you guys are waiting for your coffee break. You are ready to be done. I promised a fun
Have
talk.
a coffee break after this.
Yeah. Okay. All right. So let's go ahead and look at an example. What's the data we need? We're going to remember this. We need to have descents commute, or in other words, no descending runs with more than 2 elements. Sorry. You write this more clearly. That's an easy thing for us to see. Okay, great. So we need to look for 2 things. We don't want to be above any PIs. We'll identify our PIs first, and then we'll look to see if we have descending runs longer than 2 things. In terms of arc diagrams, that's really easy to check. You just don't want a connected component with more than 2 arcs. Okay, so let's go back to our Tamari lattice example. We kind of know the answer already, but see it in this, in like this version of the statement. I've highlighted the PIs. Let's just check that my computation is correct. This is P1 because here's my simple generator S1. And as I walk up S1, see, okay, I'm still not above S2. If I go here, I am above S2, but if I take this step, I'm not, still good. But now no matter what I try to do, I'll either be above S2 or S3. And so that is why this guy is my P1. P2 can similarly be found here, and here's P3. So we cannot be above those blue guys. And now we don't want to have an arc diagram with more than two, with a connected component consisting of more than two arcs. So this 3, 2, 1, 4 guy is not above any of the P's, but the arc diagram has a connected component with more than two arcs. We see also that the interval here between this W and pop down of W is not Boolean. It's a pentagon. It's not distributive. So it's failing also that description of this. But the three yellow guys are not above any of the P's. They don't have, they only actually have a single arc, so they're definitely going to satisfy this commuting descents business. All right, let's do one more example. Maybe I can just.
You have 1 minute.
How many minutes do I have?
1 minute.
5 minutes? 0?
One minute.
Negative 5 minutes? Okay, so actually finding P1 is almost going to totally solve this. We're going to do it the same way. Here's S1, S2, S3. We're going to be totally naive. We just walk up and check. Am I above S2 or S3? Nope, still good. I'm going to try to walk up again. This guy's bad because it's above S2. I go way over here. Oh, shoot. This one's also bad. It's above S3. So that must mean, oh, no. This was P1. I could walk up one step before I got stuck. Symmetrically, this is my P3. And then you can check no matter what you try to do for S2, if you go up even one, oh, wait, if I go up one step, oh, that is not S2. Here's my S2, good. All right, if I try to go up one step, I'm automatically above S1, and symmetrically, I'm also above S3. So I can't take any steps. I'm just stuck right at S2. That's the biggest thing above S2, which is not above either of the other two generators. And so what are the things below this? Not above these. This guy, definitely the smallest thing. And here, if we draw in our non-crossing arc diagram, I have a descent to 1 and 4, 3. And those do commute, and the connected component of the arcs we can also check. Each connected component has a single arc, and then alternatively, if you popped down here, you would see you have a little square, so we do get a Boolean interval. That guy is in the image. This guy, also in the image, not above any of the P's, has one descent, so that commutes. And definitely, if we thought about it just as from W down to pop down, that interval is Boolean. If I try to go up one more step, however, I will end up being above one of the P's. Okay, so I have a kind of cool result that relates popping in the Cambrian lattice to the weak order. It's a bit technical, so I'm going to skip over this. And I want to show you one last fun thing, which is that the image of pop in this specifically bipartite Cambrian lattice has a nice description in terms of certain Motzkin paths. So actually in the Tamari lattice, the number of things in the image is in bijection with Motzkin paths, just all Motzkin paths. In the bipartite Cambrian lattice, we're in bijection with Motzkin paths which do not have a peak at height 1. It seems like there should be fewer things in the image for these bipartite Cambrian lattices, based on what I just said, but the index is shifted. And so actually, from data, it looks like bipartite Cambrian lattices have the largest image, and the Tamari lattice, it has the smallest image in general. We do some stuff with general lattice quotients. We can find an element which takes always the longest time to sort. But I just wanted to say there's many open questions here, and there are lots of beautiful, interesting lattices. So I encourage you to try doing this game and your favorite lattice poset. Maybe we talked quite a bit recently at a conference on various flavors of new Tamari lattices, and I think some work has already been started on looking at popping in these lattice posets. And there's a really beautiful connection to representation theory, but go ahead and end here. Thank you.